Let's now dive into the ocean from the atmosphere. Typically, when we talk about the tropical dynamics of atmosphere and ocean, we assume that the deep ocean is not going to play a big part, except some new ideas are emerging, new process understanding is coming, new information is being available where the response of the upper Indian Ocean seems to be very closely connected to the Southern Ocean through this so-called meridional overturning. So maybe soon enough we will have to start worrying about deeper ocean even for the tropical climate and tropical dynamics. Okay. Let's start by looking at the standard equations we have been looking at. So the UVW equations with the continuity equation for the ocean incompressible. So when we wrote d rho dt plus 1 over rho divergence v, we were still holding on to the density being not constant or compressible. In the ocean, pretty much okay to assume that the ocean is incompressible. So we reduce the continuity equations to divergence of v equal to 0. In the atmosphere, we are mostly concerned with the pressure gradients, advection of enthalpy and momentum. So the flux is lifted from the surface or generated within the column, and momentum advection, and rotational effects, Coriolis, which we've been talking about a lot, as well as frictional forces that mostly occur at the interface of the ocean and the atmosphere. And it turns out that as the atmosphere drags its bottom on this lower surface at its base, it matters whether it's on land, which doesn't move, or on the ocean, a movable liquid, because the relative motion determines the friction, the drag between the two, and momentum transfer or angular momentum conservation. So from an angular momentum perspective, the difference on whether the bottom boundary is rigid as in land or it's moving as in the ocean will become very important. So there are, of course, interesting impacts of the mountains on the atmosphere. They are invoked a lot in the mid latitudes. In general, we consider that the atmosphere in horizontal directions is responding to pressure gradient forces on a rotating platform. So the topographic effects and the waves that arise out of that and so on are not so critical in the tropical latitudes. Getting into the ocean, we wrote before 1 over rho equal approximately to 1 over rho 0, because we can write rho as rho 0 plus delta rho, and delta rho is obviously much lower than rho 0, so 1 over rho plus delta rho is essentially 1 over rho 0, which allows us to do the Boussinesq approximation, assuming density is constant when it's associated with the buoyancy or gravitational direction. And for the ocean, this friction at the surface is very critical. Of course, also the heating and the cooling. So we need to worry about the friction, which we didn't do so much so far when we talked about the atmosphere. So in the x direction, for example, typically they are written as some eddy coefficient and d squared u dx squared. So we have tend to parameterize the frictional losses as some processes happening through the so-called eddy viscosities and eddy diffusivities. So ay d squared u dy squared and az d squared u dz squared. So then fx is essentially az d squared u dz squared for the ocean, because that's the vertical transfer of momentum from the winds into the ocean. In the meridional direction, similarly, you have az times d squared v dz squared, and in the z direction you have az d squared w dz squared, right? So that becomes very critical because ocean is forced by this friction between the wind and the ocean surface. Winds are trying to grab the surface, and the strength of the winds, fetch of the winds, and the duration of the winds end up determining how much energy actually gets into the ocean to set the ocean in motion. The scales, as opposed to the atmosphere in the ocean, are very small current speeds, 0.01 to 0.1 meter per second. Length scales remain, of course, the same, even though we will see very quickly that the boundaries that oceans have, unlike the atmosphere, which can go over around across the globe, is going to become critical. The equivalent depth, obviously order 10 to the 3 meters, but we'll see that there is a way to look at it in terms of stratification of where the ocean-atmosphere interactions happen. You can consider the layer above the thermocline as reacting with the atmosphere, and that as the equivalent depth. Obviously Coriolis ranges over 10 to the minus to 10 to the minus 4 per second for the 30 south 30 north region that we are interested in. Vertical motions order 100 meters, so we are talking about equivalent depth versus vertical scales. Density 10 to the 3 kilogram per meter cube. Delta rho is 0.003 times 10 to the 3 kilogram per meter cube. So the deviations from the mean background density is fairly small. So 1 over rho being replaced by 1 over rho 0 is perfectly valid. There is our Rossby number, which tends to be very small for the ocean, and the Ekman number is the eddy coefficient, eddy viscosity, divided by Fd squared, so that is the frictional force versus the Coriolis. It's a new number for the ocean, which is also there for the atmosphere, but much more so for the ocean. So we can simplify the system by looking at du dt minus Fv, the Coriolis, equal to pressure gradient and the energy coming in from the wind. So usually we think of this as a frictional dissipation, whereas here it's what is driving the ocean. And in the meridional direction, again, we have dv dt plus f times u equals minus 1 over rho 0 dp dy plus 1 over rho 0 d tau y dz, where tau x and tau y are of course the zonal and meridional wind stresses, and they start at above the ocean surface and then have a profile going to match the ocean currents at the surface as the ocean moves because of the winds and so on. So our favorite hydrostatic balance and the continuity equation. We tend to write d tau x dz as rho 0 az del squared u del z squared, and del tau y del z as rho 0 az del squared v del z squared, where wind stress is given by some drag coefficient times density of the air times wind speed squared. Okay, so you have tau x and tau y in that case, and we will soon write the total currents as the Ekman currents plus the geostrophic currents, right? Geostrophy requires that friction be very small, but here we are using friction to drive the ocean, so obviously Ekman currents are important, and we'll see that the Ekman currents set up the tilting of the isopycnals or the sea surface, which creates gravitational flow down the hill, and then Coriolis acts on top of that, or interior there is Ekman pumping, velocity of water pumping into the interior from the Ekman layer, which sets off interior geostrophic motion. So we have V equals VE plus VG as well. Okay, so let me stop that there and explain this Ekman forcing creating the motion in the upper ocean in the low latitudes.